we're going to talk about quantifying things a little bit more with charge now, as well as talking more about Coulomb's law. So let's say I say an object Q has a charge of negative, 6.4 times 10 to the negative 18th coulombs. Well, what could you tell me about that object? All right, well, that object is negative. What does it mean to be negative? Oh, an object becomes negative, it has gained electrons. So this thing has an excess of electrons. All right, so any negative object has an excess of electrons. The question is, how many excess electrons? Oh, well, I know that the charge on each electron is negative 1.6 times 10 to the negative 19th coulombs, right? So I can then say, all right, well, how many excess electrons? Negative 6.4 times 10 to the negative 18th coulombs. And then that has a charge of, or rather each electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. We throw that all in our calculator. And we can figure out, so 6.4 exponent negative 18. These numbers are all really tiny, so I have to get used to using my magical EE button or EXP button that we used when things were very large. And we find out that the answer is 40. So that thing has an excess of electrons. Specifically, it has 40 extra electrons. Oh, 40 extra electrons. So we can actually rewrite this as well, folks, in terms of elementary charge. The charge of this thing in elementary charges is negative 40 E. Now notice here, I'm not going E minus because I'm not saying negative 40 electrons. I'm saying it has a charge of negative 40 elementary charges. Okay, so let's look at another example. Let's say Q is equal to plus 31 E. Oh, so it's a positive thing. This thing must be missing electrons. Well, how many is it missing? Oh, it's missing 31 electrons. Well, what is the charge of this thing in coulombs? Well, I know that each E is 1.6 times 10 to the negative 19th coulombs, and so I can multiply that out, 31 times 1.6 exponent negative 19, and I get 4.96 times 10 to the negative 18th coulombs, and it's positive there, okay? So I can convert back and forth between coulombs and elementary charges by using my conversion factor of 1.6 times 10 to the negative 19th coulombs per elementary charge. If you want to think of this as a conversion here, let's ignore this negative sign, right? Because this is coulombs per 1E, and I end up with negative 40E. This is 1.6 times 10 to the negative 19th per 1E, and this is E, and I end up with that, right? So I can use that conversion factor of 1.6 times 10 to the negative 19th coulombs per 1 elementary charge in this to go from something in elementary charges to coulombs, or 1E in 1.6 times 10 to the negative 19th coulombs if I have coulombs and I want to go to elementary charges. So these are my conversion factors there that I'm multiplying by, okay? All right, so let's look at another. Let's say Q is equal to positive, 8.4 times 10 to the negative 17th coulombs. I don't know. All right. Well, what happened to that? Okay, well, this thing is apparently has missing electrons. If we convert this into number of elementary charges, we can see how many pretty easily. So let's do that conversion. So we're going to take that, we're going to multiply it by our conversion factor here, 1E, 1.6 times 10 to the negative 19th coulombs, and we find 8.4 exponent negative 17 divided by 1.6 exponent negative 19. We get 525 positive E. So this thing must be missing 525 electrons in order to do that. Okay, great. Let's just do one more. Let's say Q is equal to -9 times 10 to the -19th coulombs. Okay, well, here we go. This thing must have excess electrons. Let's convert this into elementary charges so we can see how many excess electrons it has, right? So I'm going to multiply this by 1e over 1.6 times 10 to the -19th coulombs in order to find that. So there we go, 19 divided by 1.6, exponent -19, and we get -5.625e, right? So this thing, must have an excess of 5.625 electrons, right? Okay, awesome, right? Everyone's good with that, right? Right? Hopefully you're kind of yelling at me and at the screen because that should not look right to you. Because the answer is how could you have this? Because an electron is a thing. The only way this happens is if you could lose or gain a part of an electron, and you can't. There's a reason why an electron is called an elementary charge. An electron cannot be split, okay? That's what it means to be an elementary charge. So that has a weird implication. If I can only lose electrons or gain electrons, that must mean that this amount of charge actually, I'm going to do this in red, does not occur in nature. That does not exist. Charge apparently can only occur in multiples of the elementary charge. Because either you lose a full electron or gain a full electron. So that notion is going to have a name. So the idea is that charge can only occur in integer multiples of the elementary charge. And that is something called the quantization of charge. Another way to phrase that quantization of charge, you can say the sentence, charge is quantized. Quantized is a word that means only occurs in specific amounts. Give you another example of something that's quantized. US money, physical money, is quantized because you can't have less than a penny, right? Like there don't exist coins anymore that are worth less than half a penny, so all your physical money has to be in integer multiples of pennies. Now we know, like the stock market and whatnot, and digitizing our currency has allowed us to go down to parts of a penny, or you go to the gas station and there's a 9/10 on that, but you can't physically have that. So that was what my statement was. Physical US money is quantized. Something only occurs in specific amounts. Hopefully you've heard of that notion before. In chemistry last year, the orbitals for where electrons exist around a nucleus were in quantized orbitals, that they existed only at specific spots and not at other spots, okay? So there you go, the quantization of charge. The second thing I want to deal with in this video is go through the notion of Coulomb's law a little bit more. So Coulomb's law is the thing that talks about the electrostatic force. We've already said some things about that force. The first thing we said is that it is a non-contact force. What's another way of saying that? Yep, this is a fundamental force. As a fundamental force, it is also a conservative force, meaning when it does work, the energy of a system does not change. It just changes from potential to kinetic or kinetic to potential. That means associated with this is a potential energy, right, which we will call later EPE. We'll come back to that. So fundamental force, non-contact, conservative, energy is conserved when this force does work, associated with potential energy. Cool. Now, a couple of other things we saw about it. We said that the more strongly an object was charged, the greater the force. Well, hopefully that sounded to you like a direct relationship. But here's the thing. How many things do you need in order to see Coulomb's law? You needed two of them, right? So we had two objects. So the force is going to be directly proportional to each of the charges, but specifically to the magnitude of each of the charges. So we'll say the magnitude of this force is directly proportional to each of the charges. We're not going to get carried away with the negative and positive signs in this. The other thing we saw was the closer things were, the stronger the force. What does that remind you of? Well, hopefully you said that reminds us of a inverse type relationship. But hopefully what you saw when you did this demo is that when you brought the things closer, let's say they were going to attract. You brought them closer, they attracted. And then when you got really close, all of a sudden they attracted a lot. So not just that as you got closer, the force got bigger, but as you got closer, the force got a lot bigger. Hopefully that reminds you of a specific type of law, and that's going to be an inverse square law with the distance, where r is the distance between center to center of the object. When we put all these things together, boom, we get that this force, which we're going to call Fe, the electrostatic force, we don't want to say Fc because people use that for the centripetal force, is directly proportional to Q1, Q2 over r squared. I don't need the magnitude signs around r because r is a distance, right? So there we go. If I want to turn that into an equation, I put a constant in front of that. So K, Q1, Q2 over r squared. And it was people back in the days of Coulomb and whatnot that they came up with that value of K so that they could do calculations, right? And figure out what the size of charges is. So we're just going to know K is something called the electrostatic constant. And it can be found on the tables. And so what you're going to see on the tables is 8.99 times 10 to the 9th newtons meters squared over coulombs squared. Now that number's a pain in the ass because it's so close to a nice number. So when we do our work, folks, we're just going to actually just go to 2 sig figs on this to keep our life easier. 9 times 10 to the 9th newtons meters squared over coulombs squared. So this equation is the expression of Coulomb's law, and we can use this to calculate things. So a couple of things about this. One, when we plug into this, our R has to be in meters, our Q's have to be in coulombs, not in terms of elementary charges, okay? Second, this equation only gets for us what the size of the force is. It does not get for us the direction of the force. What we're going to do is use our understanding of like charges repel and opposite charges attract in order to figure out the direction of forces. So we're going to have to use context and logic in order to figure out the directions of the force. The math is not going to give us the directions of the force, right? So let's not get into that. So there you go. This is how we do Coulomb's law. We can use this in order to start doing some simple calculations with this. And we'll get back to talking about something at the end of the next section. Because if you look at that law, it should remind you a lot. In fact, a lot of these things on this page should remind you a lot of something. Anyone else know another fundamental force that's a conservative force that's associated with a potential energy that's directly proportional to some things, the product of some things, and inversely proportional to the distance squared between? And hopefully you're thinking the gravity force, which has remember the format Fg is equal to big G m1 m2 over r squared. But there's some fundamental differences between these two types of forces, even though there's a lot of similarity. And we're going to come back later to do an explicit comparison of the force of gravity and the electrostatics force after we see a little bit more about how charge works.